On the morning of January 15th, 2026, a research team monitoring deep space telemetry from the Parker Solar Probe noticed something that shouldn't exist. The spacecraft's magnetometer, designed to study the Sun's magnetic environment, had picked up an anomalous reading while passing near the trajectory of 3I Atlas. The signal was clear, repeating, and coming from a source that had no business generating magnetic fields. Comets don't do this. Asteroids don't do this. Inert chunks of ice and rock drifting through space simply don't produce their own magnetism. The initial assumption was instrument malfunction. Space is harsh. Radiation degrades sensors, and false readings happen. But the Parker Solar Probe's magnetometer had been operating flawlessly for years, measuring the Sun's complex magnetic topology with precision that revolutionized our understanding of solar wind dynamics. A sudden failure seemed unlikely, but protocol demanded verification. The team ran diagnostics, checked calibration data, and examined every possible source of error. Everything came back nominal. The instrument was working perfectly, which meant the impossible reading was real. Within hours, other facilities began checking their data. The solar orbiter, positioned differently in its elliptical path around the Sun, confirmed similar magnetic signatures when its trajectory brought it within range of 3I Atlas's position. Now, two independent spacecraft, built by different space agencies with different instruments, were reporting the same phenomenon. The odds of simultaneous malfunction dropped to statistical impossibility. Ground-based observatories with sensitive magnetometers joined the effort, though detecting such signals from Earth's surface through our planet's own magnetic interference presented enormous challenges. By January 17th, the astronomy community was quietly circulating preliminary reports through private channels. No press releases yet, no public announcements, just careful sharing of data among trusted colleagues. The readings showed a magnetic field strength far exceeding anything expected from induced magnetization or interaction with the solar wind. This wasn't 3I Atlas passively responding to external magnetic fields like a piece of iron near a magnet. This was active field generation, emanating from within the object itself. The implications hit like a shockwave. Every model of interstellar object composition, every understanding of how these cosmic wanderers behave, assumed they were magnetically inert. Sure, they might contain trace amounts of magnetized minerals, frozen relics from their formation billions of years ago. But those would produce weak, static fields, geological fingerprints locked in stone. What the instruments were detecting was dynamic, fluctuating, and orders of magnitude stronger than residual magnetization could explain. Something inside 3I Atlas was generating inside magnetic field right now, in real time, as it journeyed through our solar system. And nobody could explain how or why. The silent giant had just become significantly less silent, speaking in a language written in electromagnetic force, delivering a message that challenged everything we thought we knew about objects from beyond our sun. The embargo broke on January the 21st, 2026. 3 major observatories issued coordinated statements confirming detection of an intrinsic magnetic field originating from 3I Atlas. The European Space Agency went first, releasing telemetry data from Solar Orbiter showing unambiguous magnetic signatures correlated with the object's position. NASA followed within the hour, presenting Parker Solar Probe measurements that matched the European findings with remarkable precision. The Harvard-Smithsonian Center for Astrophysics, which had been tracking 3I Atlas since its discovery, added ground-based observations supporting the spacecraft data. The scientific community's reaction was immediate and intense. Within minutes of the announcements, astronomy forums exploded with discussion. Researchers who had spent months analyzing 3I Atlas's mass and chemical composition suddenly found themselves confronting an entirely new category of anomaly. The object that had already challenged models with its unexpected size and exotic volatiles now presented a phenomenon that shouldn't be physically possible, given our understanding of how cold, inert bodies behave in space. Press conferences convened rapidly across multiple time zones. The tone was carefully measured, emphasizing preliminary nature of findings while acknowledging the extraordinary implications. Scientists stressed that peer review hadn't yet occurred, that alternative explanations needed thorough investigation, that jumping to conclusions would be premature. But even through the cautious language, excitement was palpable. This was genuinely unexpected. This was the kind of observation that rewrites textbooks. Media coverage spread globally within hours. Headlines ranged from measured scientific reporting to breathless speculation. Some outlets focused on the technical achievement of detecting such signals across vast distances. Others immediately raised questions about what could generate magnetism in an interstellar object. A few jumped straight to implications that responsible scientists were carefully avoiding in official statements. The viral nature of the story reflected both legitimate scientific interest and the human tendency to find mystery irresistible. Social media amplified every angle. Amateur astronomers shared their own attempts to detect the field using backyard equipment. Science communicators created explainer threads about planetary magnetism and dynamo theory. Speculation about artificial origins began circulating almost immediately, though the scientific community pushed back firmly against premature, extraordinary claims. The conversation demonstrated both public engagement with genuine discovery and the challenge of maintaining nuance when dealing with anomalous observations. By January the 23rd, over 50 research institutions had requested observing time on various instruments to study 3I Atlas's magnetic properties. The object that had been scientifically interesting was now absolutely critical. Telescopes were being redirected, observation schedules rearranged, and collaborative networks formed at unprecedented speed. The astronomy community was mobilizing to understand something that threatened fundamental assumptions about interstellar visitors. 3I Atlas had broken its silence in the most unexpected way possible, and the world was listening. To understand why magnetometer readings from 3I Atlas sent shockwaves through the scientific community, we need to grasp what magnetic fields tell us about celestial objects. Planets like Earth generate their own magnetism through dynamo action, a process requiring liquid metallic cores, internal heat, and rotation. The churning motion of conductive fluids creates electric currents, which produce magnetic fields. It's elegant physics, well understood, and absolutely dependent on specific internal conditions that small bodies simply don't possess. Comets and asteroids lack these requirements entirely. They're cold, mostly solid, and far too small to retain the primordial heat needed for molten interiors. Any magnetism they display comes from frozen relics, ancient magnetic minerals locked into their structure during formation billions of years ago. These residual fields are weak static and unchanging. They're geological fossils, not active processes. When spacecraft visit comets, their magnetometers detect essentially nothing beyond faint traces of mineral magnetization and the comet's interaction with solar wind. 3I Atlas appeared to be following this script perfectly until January 2026. Its composition matched expectations for an interstellar comet, showing water ice, carbon dioxide, and exotic volatiles consistent with formation in the frigid outer regions of some distant solar system. Its behavior, despite the mass anomaly, suggested a natural object shaped by billions of years of cosmic wandering. Nothing about its outgassing patterns, spectroscopic signature, or thermal profile hinted at internal activity beyond passive warming from solar radiation. Active magnetic field generation changes this picture fundamentally. It implies energy sources we haven't accounted for, internal structures we didn't predict, or physical processes we don't understand. The energy budget becomes critically important. Generating a measurable magnetic field requires power, sustained over time. Where is that power coming from? Comets don't have engines. They don't carry fuel. They're supposed to be inert debris, warmed temporarily by stellar approach, but otherwise dead worlds carrying no internal dynamism. The implications cascade outward rapidly. If 3I Atlas can generate its own magnetic field, our models of interstellar object composition need revision. If it possesses internal heat sources sufficient for such activity, we need to identify what those sources are and why they weren't obvious in earlier observations. If it's rotating in ways that enable dynamo action, we need to explain how an object this size maintains such rotation, and what kind of internal structure would support conductive fluid motion. Every assumption about what drifts between the stars suddenly becomes questionable. Are other interstellar visitors equally active internally? Did we miss similar signatures from Oumuamua or 2I Borisov because we weren't looking for them? How many of our fundamental beliefs about cosmic debris rest on incomplete observations of objects we thought we understood? 3I Atlas just transformed from an interesting anomaly into a challenge against the very foundations of planetary science and our understanding of what exists in the space between stars. The Parker Solar Probe wasn't looking for 3I Atlas when it detected the anomaly. Launched in 2018, the spacecraft's mission focused exclusively on studying the Sun's outer atmosphere and solving decades-old mysteries about solar wind acceleration and coronal heating. Its highly elliptical orbit brings it closer to our star than any previous human-made object, enduring temperatures exceeding 1000 degrees Celsius while collecting data that's revolutionizing solar physics. On January 15th, 2026, during its routine data transmission window, the probe's magnetometer logs included something unexpected buried in the standard measurements. The anomaly appeared as a localized magnetic enhancement that didn't match any known solar phenomenon. The signature was too coherent, too persistent, and positioned wrong relative to the Sun's magnetic field lines. Initial automated analysis flagged it as potential instrument noise or data corruption during transmission. But when mission scientists examined the raw telemetry, the signal's characteristics looked remarkably clean. No static, no dropout patterns, no artifacts typical of sensor malfunction or communication errors. The magnetometer had detected something real. Orbital mechanics placed the Parker Solar Probe within 10 million kilometers of 3I Atlas's trajectory at the time of detection. That's close by space standards, though still a considerable distance. The probe's magnetometer, designed to measure the Sun's powerful magnetic environment, was sensitive enough to detect fields far weaker than solar background levels. When researchers plotted the anomalous signal's direction vector, it pointed directly toward where 3I Atlas should be, according to updated trajectory calculations, incorporating recent astrometric measurements from ground-based telescopes. Confirmation protocols began immediately. The team pulled archived data from previous orbits when the probe had passed near other comets and asteroids. None showed similar signatures. They examined the spacecraft's own magnetic environment, checking whether internal systems could somehow generate false readings. Everything pointed to an external source. They calculated whether solar wind interactions with 3I Atlas's outgassing could produce detectable magnetic signatures at that distance. The physics didn't work out. Plasma sheaths around comets create local effects, but nothing that would register on instruments 10 million kilometers away. By January 16th, the Parker Solar Probe team had drafted a preliminary report for internal circulation among NASA's Heliophysics division. The document outlined detection parameters, ruled out obvious artifacts, and noted the spatial correlation with 3I Atlas. It stopped short of definitive conclusions, instead recommending that other spacecraft with magnetometers be tasked to observe the interstellar visitor during their orbital windows. The tone was cautious, professional, and emphasized the need for independent verification before making any public statements. But between the careful scientific language, the implications were clear. They detected something coming from 3I Atlas that shouldn't exist, something that challenged basic assumptions about what interstellar objects are and how they behave. The first thread had been pulled, and the entire fabric of understanding was beginning to unravel. The first instinct when facing impossible data is to question the instruments, not reality. Space operates on well-established principles, and magnetometers occasionally produce false readings from cosmic ray impacts, solar particle events, or electronic glitches. The Parker Solar Probe team spent 48 hours methodically eliminating every mundane explanation before accepting that something genuinely anomalous was occurring. Each conventional possibility was tested against the data and found wanting. Instrument malfunction topped the list of likely culprits. Magnetometers in space face constant bombardment from high-energy particles that can temporarily disrupt sensors or create phantom signals. The team examined telemetry from the probe's other instruments during the detection window, looking for evidence of particle strikes or radiation spikes. Nothing correlated with the magnetic readings. The spacecraft's housekeeping data showed all systems operating within normal parameters. Temperature, voltage, and calibration metrics remained stable throughout the observation period. If this was equipment failure, it was the cleanest, most selective malfunction on record. Solar wind interactions provided another potential explanation. When comets approach the Sun, their outgassing creates ion clouds that interact with charged particles streaming from our star. These interactions can generate localized magnetic structures called induced magnetospheres. However, calculations showed 3I Atlas was too distant from the Parker Solar Probe for induced effects to register at the measured intensity. The inverse square law is unforgiving. Magnetic field strength drops rapidly with distance. For the probe to detect an induced magnetosphere around 3I Atlas at 10 million kilometers. The comet would need outgassing rates thousands of times higher than observations indicated. Background interference from the Sun itself seemed plausible initially. The solar magnetic field is complex, twisted by rotation and solar wind dynamics into intricate patterns. Could the probe have detected an unusual solar structure that coincidentally aligned with 3I Atlas's position? Extensive modelling of solar magnetic topology during the observation window ruled this out. The detected signature's characteristics didn't match solar field properties. The orientation was wrong, the variability patterns differed, and the signal's coherence exceeded what solar turbulence would produce. Remnant magnetization offered perhaps the most scientifically reasonable explanation. Some asteroids contain iron-rich minerals that preserve ancient magnetic fields from their formation era. Could 3I Atlas carry particularly strong magnetic minerals? The problem was intensity and behavior. Remnant fields are static and weak. They don't fluctuate. They don't strengthen over time. The Parker Solar Probe detected a dynamic signal that varied in measurable ways over hours. That behavior pattern matched active field generation, not geological fossils frozen in rock. By January 17th, every conventional explanation had been systematically dismantled. The data remained stubbornly real, verified through multiple analysis methods, and cross-checked against decades of spacecraft magnetometer observations. The impossible reading wasn't instrument error, solar contamination, plasma interactions, or mineral magnetization. It was something else entirely, something that demanded acknowledgement regardless of how uncomfortable the implications became. Science had reached the point where avoiding the obvious conclusion required more assumptions than accepting it. The magnetic field emanating from 3I Atlas measured approximately 500 nanotesla at the Parker Solar Probe's position, roughly 1% of Earth's surface magnetic field strength. That might sound weak until you account for distance. The probe detected this signal from 10 million kilometers away. Magnetic field intensity follows an inverse cube law for dipole sources, meaning it weakens dramatically with distance. Working backward through the mathematics, researchers calculated that at 3I Atlas's surface, the field strength could reach anywhere from 50 to 200 microtesla, depending on the field's exact geometry and source distribution. To put those numbers in perspective, Earth's magnetic field at the surface measures about 50 microtesla at the equator. We're talking about an interstellar object potentially generating a magnetic field comparable to an entire planet. This is where the impossibility becomes visceral. Earth achieves its magnetism through a liquid iron outer core 2,000 kilometers thick, heated by radioactive decay and primordial formation energy, spinning with the planet's rotation to create a self-sustaining dynamo. The process requires planetary scale mass, internal temperatures exceeding 4,000 degrees Celsius, and billions of years of geological evolution. 3I Atlas is a comet-sized object, perhaps 5 to 10 kilometers across, based on mass estimates and outgassing observations. It should be cold inside, approaching the temperature of interstellar space before solar warming. It lacks the mass to retain significant primordial heat or sustain radioactive decay chains capable of melting metals. Its rotation rate, measured through photometric variations in reflected sunlight, shows nothing unusual that might drive exotic dynamo processes. By every conventional metric, this object should be magnetically dead, contributing nothing to local magnetic field measurements beyond perhaps a whisper of frozen mineral magnetization. The energy budget becomes the critical constraint. Generating a 50 microtesla field requires substantial power input, sustained continuously. Earth's dynamo operates on roughly 1 terawatt of power, drawing from the planet's vast internal heat reservoir. Scale that down to 3 I-Atlases size while maintaining comparable field strength, and you still need power outputs that dwarf anything a passive comet could provide. Solar heating can't do it. The energy absorbed from sunlight at 3 I-Atlases current distance isn't remotely sufficient. Radioactive decay would require concentrations of unstable isotopes far beyond anything observed in natural solar system formation. Chemical energy from exotic reactions also falls short. Even if 3 I-Atlases' interior contained reactive compounds capable of generating heat, the energy density and reaction rates needed to sustain dynamo action exceed plausible bounds. You'd essentially need a comet filled with rocket fuel, burning continuously, which contradicts everything we know about how these objects form and what they're made of. The strength of the detected magnetic field, combined with 3 I-Atlases' modest size, creates an energy paradox that refuses resolution through known physics. Something is powering this field, and that something has no obvious place in our current understanding of how matter behaves in space. The magnetic field wasn't static. This realization emerged during the first week of intensive monitoring following the public announcements. Multiple spacecraft tracking 3 I-Atlas at different orbital positions detected variations in field strength that correlated across platforms. The changes weren't random noise or measurement uncertainty. They followed patterns, rising and falling over periods ranging from hours to days. Something about the magnetic generation process was dynamic, responding to conditions, or driven by internal mechanisms that operated on timescales accessible to human observation. Initial data from late January 2026 showed baseline field strength fluctuating by approximately 15 to 20% over 6-hour intervals. The Parker Solar Probe, maintaining its solar observation mission while opportunistically monitoring 3 I-Atlas during trajectory windows, recorded these oscillations with remarkable clarity. Solar Orbiter, positioned differently relative to both the Sun and the interstellar visitor, confirmed similar patterns offset by light travel time delays. The concordance between independent measurements eliminated any remaining doubt about instrumental artifacts. The field was genuinely variable. By early February, longer-term trends became apparent. The overall magnetic field strength was increasing gradually as 3 I-Atlas continued its journey through the inner solar system. Analysis of archived data from January showed the field measured approximately 30% weaker during initial detection compared to late February observations. This strengthening correlated loosely with the object's decreasing distance from the Sun and corresponding increase in solar heating, though the relationship wasn't perfectly linear. Something about warming appeared to enhance magnetic generation, but the mechanism remained mysterious. Short-period variations displayed intriguing quasi-periodic behavior. Spectral analysis of continuous magnetometer data revealed dominant fluctuation cycles near 5.3 hours and 12.7 hours. These periods didn't match 3 I-Atlas's known rotation rate, measured photometrically at roughly 18 hours. The magnetic oscillations were beating to a different drum. suggesting internal processes decoupled from simple surface rotation. Perhaps convection cells in a hypothetical liquid layer, resonant modes in the object's interior, or cyclic chemical reactions driving electrical currents. Most puzzling were occasional sharp transients, brief spikes in field strength lasting minutes to an hour before returning to baseline levels. These events occurred irregularly, perhaps 3 to 5 times per week, based on available coverage. Their unpredictability made them difficult to study, requiring continuous monitoring that stretched observational resources. Some transients correlated with observed increases in outgassing activity, visible as brightness surges in optical and infrared observations. Others happened during periods of apparent quiescence, suggesting multiple triggering mechanisms or complex internal dynamics. The temporal evolution transformed 3I Atlas from a puzzle into an active laboratory. This wasn't ancient magnetism frozen into rock or steady-state processes running unchanged for millennia. This was happening now, evolving in response to conditions, displaying complexity that hinted at sophisticated internal structure. Each new data point added detail to a picture that became more mysterious with clarity. The magnetic field was alive in some functional sense, breathing with rhythms that spoke of processes science couldn't yet identify or explain. Planetary dynamos represent our best understood mechanism for generating strong magnetic fields. Earth, Jupiter, Saturn, and several other solar system bodies maintain their magnetism through this process. If 3I Atlas possessed a similar system, it would explain the observations while staying within conventional physics. The challenge lies in making the requirements fit an object that by all appearances shouldn't meet them. But desperate times call for creative modelling, and the astronomy community began exploring whether a comet-sized body could somehow sustain dynamo action. The basic requirements are straightforward. You need a conductive fluid, typically molten metal or metallic hydrogen, under extreme pressure. You need that fluid to move in organized patterns, usually driven by convection as hot material rises and cool material sinks. You need rotation to twist the flow into helical patterns through Coriolis forces, and you need sufficient volume and conductivity for the process to become self-sustaining, where magnetic fields induce currents that strengthen those same fields. It's elegant when everything aligns properly. 3I Atlas presents problems at every step. First, the mass. Even accepting the high-end estimates of 33 trillion kilograms, this object lacks the gravitational compression needed to maintain molten metallic cores. Earth's outer core exists under pressures exceeding 130 gigapascals, enough to keep iron liquid despite temperatures that would vaporize it at surface conditions. 3I Atlas's interior pressure barely reaches a few megapascals, similar to deep ocean trenches on Earth. Metals stay solid at those conditions unless heated to melting points that require external energy sources. The heat budget remains the critical constraint. Earth's dynamo draws power from several sources, including radioactive decay of uranium, thorium, and potassium, distributed throughout the mantle, plus residual heat from planetary formation and crystallization energy released as the inner core slowly solidifies. These processes have operated for 4.5 billion years, gradually depleting, but still providing roughly 1 terawatt of power. 3I Atlas would need comparable power density, scaled to its much smaller volume. Where does that energy come from? Theoretical models began exploring exotic compositions. What if the object's interior contained unusually high concentrations of radioactive isotopes, perhaps enriched through unknown formation processes? Calculations showed you'd need radioactivity levels that would make the surface detectably warm and generate characteristic gamma-ray signatures. Observations showed neither. What if phase separation during formation created a dense metallic core surrounded by lighter ices, maximizing gravitational energy available for conversion to heat? The mass and moment of inertia measurements didn't support such extreme differentiation. Rotation rates provided another mismatch. Effective dynamos typically require relatively rapid spin to generate sufficient Coriolis effects. 3I Atlas rotates once every 18 hours, slower than Earth, but not impossibly so. However, the observed magnetic field variations didn't follow the rotation period, suggesting either the dynamo operated independently of bulk rotation, or something else entirely was happening. The hypothesis remained on the table because eliminating it required proving a negative. But with each passing analysis, the dynamo explanation looked less like a solution and more like wishful thinking, trying to force familiar physics onto an unfamiliar phenomenon. Energy doesn't appear from nowhere. This fundamental principle of thermodynamics creates the most severe constraint on any explanation for 3I Atlas's magnetic field. Generating and maintaining magnetism requires power, measurable in watts, drawn from some reservoir that must be identified and quantified. When researchers attempted to balance the energy budget for a hypothetical dynamo inside 3I Atlas, the numbers refused to cooperate. Every calculation revealed deficits that couldn't be filled by known processes. Start with radioactive decay, the power source sustaining Earth's internal heat over billions of years. Natural radioactivity comes primarily from isotopes of uranium, thorium, and potassium scattered through rocky material. Average solar system composition provides baseline expectations for how much radioactive material an object should contain. 3I Atlas, based on spectroscopic analysis showing water ice and carbon compounds, appears more like a comet than a rocky asteroid. Comets typically contain minimal radioactive elements because they formed in cold outer regions where rocky material was scarce. Even granting generous assumptions about rocky component fraction, calculations showed radioactive decay in a 5-kilometer object would produce perhaps a few megawatts of heat. That's enough to slightly warm the interior above ambient space temperature. It's nowhere near the gigawatts needed to maintain a molten metallic core and drive dynamo circulation. You'd need radioactive concentrations hundreds of times higher than any natural solar system body, approaching levels found in uranium ore deposits. Such enrichment has no plausible formation mechanism and would produce detectable radiation signatures that observations don't show. Primordial heat from formation offered another potential source. When objects form through collisional accretion, gravitational potential energy converts to thermal energy, heating the interior. Planets retain this heat for billions of years because heat loss scales with surface area, while heat content scales with volume. Larger objects cool more slowly. 3I Atlas is tiny by planetary standards. Any formation heat would have radiated away within millions of years maximum. The object has likely been wandering through interstellar space for billions of years, more than enough time to reach thermal equilibrium with the 3 Kelvin cosmic background radiation. Chemical energy from exotic reactions seemed worth exploring. Could 3I Atlas contain reactive compounds that generate heat when mixed or exposed to changing conditions during solar approach. The energy density of chemical reactions, even highly energetic ones, provides far less power than needed. You'd essentially need the entire object to be fuel-burning continuously. Moreover, such reactions would alter the chemical composition detectably over time. The outgassing chemistry observed by JWST showed standard cometary volatiles, not evidence of ongoing energetic reactions. Tidal heating, which keeps Jupiter's moon, Io, volcanically active through orbital flexing, couldn't apply to 3I Atlas. The object travels alone through interstellar space, with no gravitational companion to generate tides. Solar tidal forces at its current distance are negligible. Every conventional energy source failed to provide sufficient power. The heat budget crisis wasn't just a minor discrepancy. It was a chasm between what physics allowed and what observations demanded. A gap that conventional explanations couldn't bridge, no matter how creatively researchers stretched assumptions. When conventional dynamo models failed to explain 3I Atlas's magnetic field, researchers turned to more exotic possibilities within known physics. Thermoelectric effects offered an intriguing alternative that didn't require molten cores or gigawatts of power. The principle is straightforward. Temperature differences across certain materials can drive electric currents directly without moving fluids. Those currents generate magnetic fields. The process operates in solid materials at relatively low power levels. Could 3I Atlas be a natural thermoelectric generator on a cosmic scale? The Seebeck effect, discovered in the early 1800s, describes how temperature gradients in conductive materials create voltage differences. Connect two different materials in a circuit with junctions at different temperatures, and current flows spontaneously. Thermoelectric generators use this principle in spacecraft power systems, converting heat from radioactive decay directly into electricity. The efficiency is modest, but the reliability is exceptional. No moving parts, no maintenance required, just patient conversion of thermal energy to electrical power. 3I Atlas experiences significant temperature variations across its surface and interior. The sunward side receives direct solar heating, while the shadow side radiates heat into space, creating gradients potentially exceeding 100 degrees. As the object rotates, these patterns shift and evolve. Internal temperature also varies with depth, as solar warming penetrates the surface layers, while deeper material remains cold from billions of years in interstellar space. These gradients could theoretically drive thermoelectric currents if the right materials existed in the right configurations. The challenge lies in material requirements and current magnitudes. Generating magnetic fields strong enough to detect from millions of kilometers requires substantial current flow through large volumes of conductive material. Most ices and rocky minerals have poor thermoelectric properties. You'd need specialized materials, perhaps metal-rich layers or exotic mineral phases with unusual electronic properties. The currents would need to flow in organized patterns rather than randomly cancelling out. Natural geological structures rarely provide such convenient electrical architectures. Researchers modeled various configurations, attempting to make thermoelectric generation work. Perhaps 3I Atlas contained stratified layers of different materials with varying conductivities and thermoelectric coefficients. Solar heating could drive currents in surface layers, while internal cold regions completed the circuit. Rotation would twist these currents into helical patterns capable of generating dipolar magnetic fields. The models produced fields of approximately correct magnitude, using plausible though optimistic assumptions about material properties. However, the temporal variations posed problems. Thermoelectric currents should respond smoothly to temperature changes, which vary gradually over hours as rotation shifts heating patterns. The observed magnetic field showed sudden transients and quasi-periodic oscillations that didn't correlate well with expected thermal evolution. The 5.3-hour and 12.7-hour periodicities in magnetic variations had no obvious thermal explanation. Temperature patterns should follow the 18-hour rotation period much more closely. The thermoelectric hypothesis remained viable as a partial explanation or contributing factor. Perhaps it provided baseline field strength, while other processes drove variations. But as a complete solution, it shared the dynamo's weakness. Creative physics could generate magnetic fields at appropriate scales, but the detailed behavior refused to match predictions. 3I Atlas kept displaying complexity that exceeded what even exotic natural processes should produce. Comets create their own miniature magnetospheres through interactions between outgassing and the solar wind. This is established physics, observed countless times by spacecraft visiting active comets. When solar ultraviolet radiation ionizes sublimating gases around a comet's nucleus, the resulting plasma interacts with magnetic fields carried by the solar wind. The interaction creates complex electromagnetic structures, including bow shocks, current sheets, and induced magnetic fields. Could 3I Atlas simply be displaying an unusually strong version of these well-understood processes? The appeal of plasma interaction models lies in their reliance on conventional comet physics. No exotic internal structures required, no mysterious energy sources, just standard solar wind dynamics playing out around an object that happens to be very active and unusually massive. 3I Atlas shows vigorous outgassing, with production rates estimated around 150 kilograms per second based on JWST observations. That's substantial, creating an extensive coma of gas and dust that could support plasma interactions visible to distant magnetometers. Detailed modeling began in late February 2026 as researchers attempted to reproduce observed magnetic signatures through pure interaction effects. They input 3I Atlas's known outgassing rates, composition data, rotation period, and trajectory through the heliosphere. Solar wind conditions during observation windows came from multiple solar monitoring spacecraft. The models calculated expected plasma densities, ionization rates, and resulting magnetic field configurations around the comet. The results were encouraging initially. Plasma interactions could generate fields in the general range of observed strengths under optimistic assumptions about ionization efficiency and current flow patterns. The induced magnetosphere extended far enough that spacecraft at millions of kilometers could plausibly detect it. The basic physics worked, but details undermined the simple explanation. Induced magnetospheres are inherently tied to solar wind conditions. When the wind strengthens, induced fields strengthen proportionally. When the wind weakens or its magnetic orientation shifts, induced fields respond within minutes to hours. 3I Atlas's magnetic field didn't show this behavior. Continuous monitoring revealed variations that bore no correlation to solar wind measurements. On February 8th, for example, solar wind speed increased by 30%, and magnetic field strength doubled over a 6-hour period. 3 eye atlases detected magnetic field actually weakened slightly during this interval. Similar mismatches appeared throughout the dataset. The comet's magnetism seemed decoupled from solar conditions, varying according to its own internal clock, rather than external forcing. The geometry also caused problems. Induced magnetospheres arrange themselves predictably relative to the sun and solar wind direction. The field lines drape around the comet in characteristic patterns that have been mapped extensively at other comets. 3 eye atlases field appeared more dipolar, resembling intrinsic planetary magnetism rather than draped-induced structures. Multiple spacecraft at different viewing angles should have seen different field orientations if this was purely interaction effects. Instead, they detected consistent dipole geometry, suggesting a single source within the object itself. Plasma interactions certainly occurred around 3 eye atlas. The object was active and surrounded by ionized gas interacting with solar wind. But these processes appeared as minor perturbations on a dominant intrinsic field, rather than generating the field themselves. Once again, conventional comet physics could explain part of the picture, but failed to account for the full phenomenon. If 3 eye atlas needed internal heat to power a dynamo or drive thermoelectric currents, radioactivity provided the most straightforward natural source, but not the dispersed traces of uranium and thorium found in typical rocky material. Something far more concentrated would be required, a core enriched with radioactive isotopes to levels that approached nuclear reactor conditions. The scenario sounded extreme, but eliminating it required showing why such enrichment couldn't occur through natural processes. Formation mechanisms offered one pathway to concentration. When stellar systems form from collapsing molecular clouds, heavier elements, including radioactive isotopes, distribute unevenly. Supernova ejecta that seeded the cloud with elements beyond hydrogen and helium don't mix perfectly. Local concentrations can exceed average abundances by factors of 10 or more. If 3 eye atlas formed in a particularly enriched pocket of its parent nebula, or if dynamical processes concentrated heavy elements during accretion, radioactive material could potentially reach unusual levels. Short-lived isotopes presented another possibility. Most radioactivity in the solar system today comes from long-lived isotopes, like uranium-238, with half-lives measured in billions of years. But young stellar systems contain short-lived isotopes that decay quickly, releasing enormous energy over relatively brief periods. Aluminum-26, with a half-life of 717,000 years, heated early solar system bodies enough to melt their interiors and drive differentiation. If 3 eye atlas incorporated substantial amounts of short-lived isotopes during formation, it could have remained internally active far longer than typical comets. The problem was timing. 3 eye atlas has been wandering interstellar space for potentially billions of years based on its trajectory and the vast distances between stars. Short-lived isotopes would have decayed completely long ago. Even aluminum-26, which can keep small bodies warm for millions of years, becomes negligible after 10 half-lives, or roughly 7 million years. For radioactivity to power current magnetic field generation, it would need to come from long-lived isotopes present in extraordinarily high concentrations. Calculations showed the required enrichment levels. To generate gigawatts of heat from radioactive decay in a 5-kilometer object, you'd need uranium and thorium concentrations approaching those found in high-grade ore deposits. Not the parts per million typical of rocky asteroids, but significant weight percentages. The entire core would essentially need to be radioactive mineral, something like a natural nuclear pile, operating at low but steady power output. Detection signatures should accompany such intense radioactivity. Gamma rays from decay chains would escape the object, creating a faint but detectable glow in high-energy astronomy observations. Neutron production from certain decay pathways and secondary reactions would generate characteristic signatures. Observations showed nothing unusual. 3I Atlas appeared gamma-ray quiet, producing only the faint signals expected from cosmic ray interactions with surface material, not the distinctive spectrum of concentrated radioactive decay. The scenario remained theoretically possible if enrichment somehow occurred in just the right configuration to minimize detectable emissions while maximizing internal heating. But the combination of required conditions, lack of supporting evidence, and absence of known formation mechanisms that could produce such configurations pushed the radioactive core hypothesis toward improbability. Nature rarely conspires so conveniently to hide smoking guns while displaying their consequences so prominently. By mid-March 2026, the scientific community faced an uncomfortable reality. Every conventional explanation for 3I Atlas's magnetic field required either impossible conditions, undetected energy sources, or convenient conspiracies of circumstance. Dynamos needed molten cores without sufficient heat. Thermoelectric effects required exotic material configurations, behaving in ways that didn't match observed temporal patterns. Plasma interactions couldn't explain the dipolar geometry or independence from solar wind conditions. Radioactive cores demanded enrichment levels that should produce detectable signatures that weren't there. The standard toolkit of planetary science had been applied exhaustively and found wanting. This wasn't a situation where one or two anomalies needed explaining. Multiple independent observations contradicted expectations simultaneously. The field strength exceeded what passive processes should generate. The temporal variations showed periodicities uncorrelated with rotation or external forcing. The energy budget refused to balance using known heat sources. The dipolar geometry suggested internal organization that small cold bodies shouldn't possess. Each piece alone might be accommodated through creative modeling. Together, they formed a pattern that resisted conventional interpretation. The response from the astronomy community revealed the challenge of confronting genuinely anomalous data. Some researchers doubled down on natural explanations, arguing that insufficient information about 3I Atlas's internal structure allowed for scenarios where standard physics could still work. Perhaps the object had unusual composition or formation history that placed it outside typical parameter ranges while remaining firmly within known physics. More data would eventually resolve the mystery through conventional means. Others suggested the observations themselves required skeptical re-examination. Were the magnetic field measurements truly as robust as claimed? Could systematic errors in multiple instruments produce correlated false signals? The peer review process for key papers was ongoing, and until independent verification confirmed every aspect of the observations, some uncertainty remained justified. Extraordinary claims demanded extraordinary evidence, and the evidence, while strong, hadn't yet achieved unassailable status. A third group acknowledged that standard models appeared inadequate as currently formulated. This didn't necessarily mean abandoning established physics, but rather recognizing that gaps existed in our understanding of how matter behaves under conditions we rarely encounter. 3I Atlas might be revealing processes that occur naturally, but operate in regimes we haven't studied thoroughly. The interstellar environment could modify objects in ways that solar system bodies don't experience. Billions of years of cosmic ray exposure, passage through different interstellar medium densities, or exposure to environments near other stars might create internal structures or conditions that our models based on solar system experience couldn't anticipate. The debate remained civil but intense. What everyone agreed upon was that 3I Atlas defied easy categorization. Whether the resolution came through better conventional modeling, recognition of overlooked natural processes, or acknowledgement of something genuinely new, the object had forced planetary science to confront its assumptions. The comfortable certainty that comets were simple, well-understood objects had evaporated. In its place sat a mystery that refused to yield to standard approaches, demanding either better questions or the courage to consider answers that lay outside familiar territory. What if everything we assumed about 3I Atlas's interior was wrong? The object appeared comet-like from external observations, showing water ice, carbon dioxide, and organic compounds, consistent with formation in cold outer regions of planetary systems. But appearances can deceive. Interstellar objects potentially experience formation conditions and evolutionary histories vastly different from solar system natives. Perhaps 3I Atlas harbored internal structures that defied conventional comet architecture while remaining entirely natural. Differentiation offered one possibility. Most comets are thought to be relatively homogeneous mixtures of ice, dust, and organic material formed through gentle accumulation of particles in the outer protoplanetary disk. But 3I Atlas's enormous mass suggested either formation through more energetic processes or subsequent evolution that could drive internal reorganization. If the object experienced sufficient heating at some point in its history, denser materials would sink toward the center while lighter ices rose outward, creating a layered structure similar to terrestrial planets. A differentiated 3I Atlas could possess a rocky or metallic core surrounded by ice mantles of varying composition. This structure would provide better conditions for magnetic field generation than a homogeneous mix. The core could contain conductive minerals, or even metallic phases if temperatures reached melting points during formation, or through some subsequent heating event. Surrounding ice layers would provide electrical insulation, potentially allowing currents to flow in organized patterns, rather than dissipating randomly through the entire volume. Phase-separated chemical layers presented another intriguing scenario. Laboratory studies of ice mixtures under pressure show that different volatile compounds can separate into distinct layers based on their physical properties. Water ice might form one layer, carbon dioxide another, with methane, ammonia, and other compounds creating additional stratification. If these layers had different electrical properties, interfaces between them could act as natural capacitors or current channels, creating electromagnetic effects that wouldn't occur in uniform compositions. Fractal internal architecture offered a more exotic possibility. What if 3I Atlas wasn't a solid mass, but rather a complex assemblage of smaller components held together by mutual gravity and occasional ice bonding. Think of a rubble pile asteroid scaled up and filled with volatiles. The spaces between components could allow gas flow patterns that wouldn't exist in solid structures. Temperature differentials between sun-heated surfaces and cold interiors could drive convection through these voids. Flowing ionized gases through fractal pathways might generate currents and magnetic fields through mechanisms that solid body models wouldn't predict. Relic structures from formation environments also deserved consideration. If 3I Atlas formed in an unusual stellar environment, perhaps near a dying star with powerful magnetic fields, or within the debris disk of a stellar collision, it might have incorporated materials or structures that preserved information about those exotic conditions. Magnetic minerals aligned by ancient fields could provide frameworks for current flow. Exotic ices or mineral phases, stable only under specific formation conditions, might possess electrical properties unknown in solar system materials. Each unconventional structure remained speculative, without direct sampling or detailed internal imaging. But they shared a common theme. If we stopped assuming 3I Atlas was simply a large comet and started treating it as a potentially unique object with its own formation and evolutionary history, the space of possible explanations expanded dramatically. Sometimes, the most important step in solving a mystery is recognizing that the question itself might be framed too narrowly. Some magnetic fields don't require active generation. They can be fossils, frozen into material during formation, and preserved for billions of years, like geological records written in electromagnetic force. This process, called remanent magnetization, occurs when magnetic minerals cool through specific temperatures in the presence of external magnetic fields. The minerals lock in the field direction, creating permanent magnets that can survive indefinitely if protected from reheating or strong external fields. Could 3I Atlas carry such a primordial field, somehow amplified or reactivated during its passage through our solar system? The concept has precedent in solar system exploration. Certain meteorites exhibit strong remanent magnetization, preserving magnetic field signatures from the early solar system when our sun and planets were still forming. Some asteroids show measurable magnetic fields, despite lacking any active dynamo. These are magnetic fossils, evidence of ancient processes long extinct. The fields are typically weak and static, but they demonstrate that small bodies can retain magnetization over billions of years under the right conditions. 3I Atlas formed somewhere in the galaxy billions of years ago, possibly in a stellar environment very different from our solar system. Young stellar systems often have strong magnetic fields associated with accretion disks, stellar winds, and the chaotic dynamics of planet formation. If 3I Atlas accreted in such an environment, it could have incorporated magnetic minerals aligned by those ancient fields. The resulting remanent magnetization would be locked into the object's structure, a memory of its birth environment. The reactivation scenario adds a dynamic element to this fossil hypothesis. Perhaps 3I Atlas's magnetic minerals remained magnetically dormant during billions of years in cold interstellar space, their field lines locked but inactive. As the object approached our sun and began warming for the first time in its interstellar journey, thermal effects could partially mobilize these ancient fields. Temperature changes might allow magnetic domains in minerals to realign or respond to external influences, effectively amplifying the frozen field into something more active and detectable. However, remnant magnetization faces severe challenges explaining the observations. Fossil fields are inherently limited by the magnetic properties of minerals. Even the strongest naturally magnetic minerals, like magnetite or pyrrhotite, produce fields measured in millitesla at their surfaces. 3-eye atlases estimated surface field strength of 50 to 200 microtesla would require substantial volumes of highly magnetic material, far exceeding typical concentrations in cometary bodies. The object would need to be more like an iron meteorite than an icy comet. The temporal variations create an even more fundamental problem. Remnant fields are static by definition. They don't fluctuate over hours, don't show quasi-periodic oscillations, and don't strengthen gradually over weeks. Thermal effects might cause slow changes as the object warms, but the observed rapid transients and complex temporal patterns suggest active processes rather than passive warming of ancient magnets. Fossil magnetization might contribute to 3-eye atlas's field, providing a baseline upon which other processes build. But as a complete explanation, it falls short. The field is too strong, too variable, and too organized to be merely a preserved memory of ancient stellar environments, no matter how exotic those environments might have been. When all conventional physics fails to explain observations, researchers sometimes turn to phenomena that operate at the boundaries of established knowledge. Quantum effects typically manifest at microscopic scales, in systems cooled to near absolute zero, or under extreme conditions rarely encountered in everyday experience. But 3-eye Atlas spent billions of years in interstellar space at temperatures approaching 3 Kelvin, just degrees above absolute zero. Could quantum mechanical processes play a role in generating its mysterious magnetic field? Superconductivity represents one of quantum mechanics' most dramatic electromagnetic phenomena. Certain materials, when cooled below critical temperatures, lose all electrical resistance and exhibit perfect diamagnetism, expelling magnetic fields from their interiors through the Meissner effect. Superconducting loops can carry persistent currents indefinitely without power input, maintaining magnetic fields with no energy cost. If 3-eye Atlas contained materials capable of superconducting at temperatures achievable in deep space, those regions could theoretically sustain currents and fields over billions of years. The challenge lies in finding plausible superconducting materials in cometary compositions. Most known superconductors are metallic elements or complex compounds requiring specific crystal structures. They need cooling to temperatures ranging from a few Kelvin for conventional superconductors to perhaps 50 Kelvin for high-temperature superconductors discovered in recent decades. 3-eye Atlas contains primarily water ice, carbon dioxide, and organic compounds based on spectroscopic observations. None of these are superconductors under any known conditions. Exotic ice phases offered a potential loophole. Water ice exists in at least 18 different crystalline forms, depending on temperature and pressure. Some phases only appear under extreme conditions not found naturally. On Earth, laboratory studies continue discovering new ice structures with surprising properties. Could some exotic high-pressure ice phase, formed during 3-eye Atlas's initial accretion or through compression in its deep interior, possess unexpected electrical properties, including superconductivity? The idea remained pure speculation without experimental evidence. But the parameter space of possible ice physics contained unexplored corners. Quantum condensates represented another fringe possibility. Under extremely cold conditions, certain systems can enter collective quantum states where many particles behave as a single coherent entity. Bose-Einstein condensates, achieved in laboratories by cooling dilute gases to nanokelvins, display bizarre properties including superfluidity and unusual electromagnetic responses. Could components of 3I Atlas, preserved at near interstellar temperatures during its long journey, maintain quantum coherence in ways that generate or sustain magnetic fields? The physics required extraordinary fine-tuning. Quantum coherence is fragile, easily destroyed by thermal fluctuations or interactions with the environment. 3I Atlas was warming as it approached the Sun, experiencing temperature increases that should destroy any quantum condensates. The object's interior remained cold compared to room temperature, but warm enough to disrupt delicate quantum states maintained in laboratory conditions. Moreover, generating macroscopic magnetic fields through quantum effects would require coherence extended across enormous numbers of particles, a regime where quantum mechanics typically gives way to classical behavior. The quantum angle represented speculation at the edges of known physics, ideas that couldn't be definitively ruled out but lacked supporting evidence or clear theoretical frameworks. These scenarios served more to highlight the depth of the mystery than to provide satisfying explanations. When even quantum mechanics gets invoked, conventional understanding has reached its limits. There's an elephant in the room that needs addressing directly. Electromagnetic signatures, particularly organized magnetic fields with temporal variations, represent exactly the kind of technosignatures that SETI researchers spend their careers seeking. When a distant object displays behavior that natural explanations struggle to accommodate, the question of artificial origin inevitably arises. Not because scientists jump to alien conclusions lightly, but because intellectual honesty demands considering all possibilities when confronting genuinely anomalous observations, no matter how uncomfortable those possibilities might be. The history of interstellar object speculation began with Oumuamua in 2017. That elongated visitors' unusual acceleration as it left the solar system prompted serious scientific discussion about whether natural outgassing could fully explain the trajectory. Some researchers proposed solar radiation pressure acting on an extremely thin, sail-like structure. Others suggested the object might be artificial, designed to use starlight for propulsion. The debate remained within scientific bounds, exploring hypotheses through calculation and observation rather than assumption and wishful thinking. 2I Borisov in 2019 provided a counterpoint, behaving exactly as natural comets should behave with no anomalies requiring exotic explanations. Its appearance reassured astronomers that interstellar visitors could be perfectly ordinary, following the same physics that governs solar system objects. The universe contained both the mysterious and the mundane, and distinguishing between them required careful analysis rather than reflexive categorization. 3I Atlas occupies uncomfortable middle ground. Its enormous mass already challenged population statistics before magnetic field detection added electromagnetic anomalies to the puzzle. Each natural explanation encounters obstacles, not definitively ruling it out, but making simple natural origin increasingly complicated. Meanwhile, the characteristics that make 3I Atlas puzzling from a natural perspective active magnetic field generation, temporal variations, apparent internal organization, overlap with properties that engineered systems might display. The key word is might. Science fiction has trained us to imagine spacecraft with powerful magnetic fields for radiation shielding, with dynamos or fusion reactors providing energy, with active systems cycling through operational states. These imagined technologies produce signatures vaguely similar to what 3I Atlas displays. But vague similarity proves nothing. Natural processes we don't fully understand could produce identical signatures. The universe is vast and ancient. Operating through physics, we've only scratched the surface of understanding. Assuming artificial origin, because we lack complete natural explanations, represents failure of imagination about nature's capabilities, not evidence for technology. The techno-signature question serves a useful function by forcing rigor. If researchers want to argue 3I Atlas is natural, they need natural explanations that actually work, not just hand-waving about unknown processes. If others suggest artificial origin might explain observations better, they need to specify what evidence would distinguish engineered systems from exotic natural phenomena. The debate pushes both sides toward precision, toward testable predictions, toward the kind of careful thinking that advances understanding, regardless of which hypothesis proves correct. Science fiction meets science when imagination encounters reality. What matters is letting evidence, rather than preference, determine which interpretation survives contact with observation. If 3I Atlas were artificial, what would we expect to observe? This question isn't idle speculation, but rather a necessary exercise in hypothesis testing. Science advances by proposing competing explanations and identifying observations that distinguish between them. The technosignature hypothesis makes specific predictions about what engineered systems should display. Comparing those predictions against actual observations provides a framework for evaluation that goes beyond philosophical debate about probabilities. Power generation represents the most fundamental requirement for any active technological system. Spacecraft need energy for propulsion, communication, environmental control, and operational systems. That energy must come from somewhere, and its generation leaves signatures. Solar panels convert sunlight to electricity, but don't produce magnetic fields. Radioisotope thermoelectric generators use radioactive decay heat and create modest electromagnetic signatures already discussed in natural context. Nuclear reactors, whether fission or hypothetical fusion systems, would produce distinctive radiation signatures, including neutrons and gamma rays from specific energy ranges corresponding to nuclear processes. 3I Atlas shows no evidence of nuclear power signatures. Gamma ray observations remain consistent with cosmic ray interactions with surface material, not the characteristic spectrum from fission products or fusion reactions. Neutron detections haven't been reported despite multiple spacecraft with appropriate instruments passing within detection range. If the object harbored a nuclear reactor, it would need extraordinary shielding to suppress these signatures below detection thresholds. Possible, but adding assumptions to protect the hypothesis. Magnetic field characteristics provide another diagnostic. Engineered magnetic fields typically serve specific functions. Radiation shielding requires strong fields, extending far from the protected volume, usually configured as dipoles, or more complex multipole arrangements, calculated for optimal particle deflection. Power generation through electromagnetic induction, requires rapidly varying fields or rotating machinery, producing distinctive frequency signatures. 3I Atlas's field appears dipolar, which matches both natural dynamos and artificial shielding designs, offering no clear discrimination. The temporal variations warrant closer examination. The quasi-periodic oscillations at 5.3 and 12.7 hours could represent operational cycles if artificial. Spacecraft systems often operate on regular schedules driven by power availability, thermal management, or communication windows. However, natural processes also produce periodicities. Convection cells, chemical oscillations, or mechanical resonances generate regular cycles without requiring design. Distinguishing engineered from natural periodicity requires additional context, like correlation with other observables or mathematical signatures of control systems. Energy efficiency becomes relevant when considering sustained operation over potentially millions or billions of years. Any technology crossing interstellar distances must either carry enormous energy reserves or generate power from ambient sources. 3I Atlas's approach to our Sun could trigger reactivation of solar-powered systems dormant during interstellar cruise. The strengthening magnetic field as solar distance decreased might support this interpretation, but it equally supports natural warming, activating thermoelectric or chemical processes. The critical insight is that techno-signatures are not unique signatures. Every potentially artificial characteristic has natural analogues under some conditions. Strong magnetic fields, temporal variations, apparent organization, all appear in natural contexts. The question becomes one of probability and parsimony. Does invoking technology explain observations more economically than invoking unusual but natural conditions? Current evidence doesn't clearly favor either interpretation, which itself tells us something important. If this were obviously artificial, the signatures would be more distinctive. If obviously natural, conventional explanations would work better. Random fluctuations look different from controlled variations. This principle underlies much of signal processing and pattern recognition. Natural processes produce noise, chaos, and occasionally quasi-periodic behavior from physical resonances or feedback loops. Engineered systems display patterns reflecting design choices, optimization algorithms, and operational requirements. If 3I Atlas's magnetic field variations contained signatures of control that would provide strong evidence for artificial origin, if variations appeared random or matched natural process predictions, natural explanations would gain support. The question was whether the available data contained sufficient information to distinguish these possibilities. Statistical analysis of magnetic field time series began in late March 2026 as researchers accumulated weeks of continuous monitoring data. The first test examined simple randomness. Truly random variations follow specific statistical distributions without correlations between successive measurements. 3I Atlas's field showed clear correlations. Changes in 1 hour predicted likely changes in the next hour with better than random accuracy. This ruled out pure noise, but said nothing about cause. Both natural oscillating systems and controlled systems produce correlated time series. Power spectral analysis revealed the 5.3 and 12.7 hour periodicities prominently, along with weaker signals at other frequencies. Natural oscillations from physical resonances typically produce peaks at fundamental frequencies, plus harmonics, integer multiples of the fundamental period. 3I Atlas's spectrum didn't follow this pattern cleanly. The observed peaks weren't simple harmonic series. They could represent multiple, independent oscillating processes, each with its own period. Or they could indicate more complex dynamics, where different timescales interacted non-linearly. Entropy measures quantified the predictability of field variations. High entropy means high unpredictability and suggests random or chaotic behavior. Low entropy indicates structure and potentially control. 3I Atlas's magnetic time series showed intermediate entropy, more structured than random noise, but less predictable than simple periodic functions. This placed it in the ambiguous zone where both complex natural systems and adaptively controlled systems operate. Weather patterns on Earth show similar entropy characteristics, clearly natural, yet displaying organization that reflects underlying physical processes. Phase space reconstruction, a technique for analyzing dynamical systems, attempted to identify whether the variations followed deterministic rules or stochastic processes. The method plot system states against time delayed versions of themselves, revealing hidden structure in chaotic systems. 3I Atlas's magnetic data produced phase space portraits with suggestions of low-dimensional attractors, geometric structures indicating the system evolved along preferred trajectories rather than wandering randomly. But the data quality and duration remained marginal for definitive conclusions. Natural chaotic systems and controlled systems both produce attractors in phase space. Researchers searched for signatures of feedback control, where system outputs influence inputs to maintain desired states. Control systems often show characteristic response patterns to disturbances, recovering to set points with specific timescales. 3I Atlas's field variations after transient spikes showed recovery patterns, but whether these reflected natural relaxation processes or active control remained ambiguous. Both interpretations fit the observations adequately given measurement uncertainties. The control problem remained unsolved. Every analysis method produced results compatible with both hypotheses. The magnetic field variations showed structure exceeding random noise, but not displaying unambiguous signatures of design. Nature can be remarkably organized without conscious organization. Technology can mimic natural patterns intentionally. Without additional discriminating observations, the data alone couldn't resolve whether intelligence or physics drove 3I Atlas's electromagnetic behavior. Occam's razor states that among competing hypotheses, the one requiring fewest assumptions should be preferred. The artificial origin hypothesis for 3I Atlas requires an extraordinary stack of assumptions, each individually improbable and collectively verging on fantasy, despite the magnetic anomalies that sparked the speculation. Understanding why demands honest accounting of what the techno-signature hypothesis actually entails, beyond the appealing simplicity of saying maybe it's aliens. First, intelligent life must exist elsewhere in the galaxy. The Drake equation attempts to quantify this probability by multiplying factors, including star formation rates, planetary occurrence, and the likelihood of life emerging and evolving intelligence. Estimates span enormous ranges, from millions of technological civilizations to humanity being alone. We have exactly one confirmed example of technological intelligence, ourselves, making reliable statistical inference impossible. Assuming aliens exist represents the first major leap. Second, that intelligence must achieve interstellar travel capability, Humanity hasn't managed this, despite decades of spaceflight experience. The energy requirements for accelerating macroscopic objects to even modest fractions of light speed are staggering. 3I Atlas travels at roughly 26 kilometers per second, typical for interstellar objects, but requiring centuries to millennia for journeys between nearby stars. Any civilization launching such objects must sustain technological sophistication over timescales that dwarf recorded human history. Third, they must choose to send objects on trajectories that happen to pass through our solar system. The galaxy contains hundreds of billions of star systems. The probability of any randomly launched interstellar probe encountering our specific neighborhood is vanishingly small unless vast numbers of probes exist. If civilizations are common and each launches millions of probes, perhaps encounters become plausible. But now we're stacking assumptions, each adding improbability. Fourth, the object must be designed to mimic natural comets almost perfectly, while displaying just enough anomalous behavior to raise questions. Why? If you're trying to hide, don't generate magnetic fields. If you're announcing presence, do it unambiguously, rather than through subtle techno-signatures that admit natural explanations. The middle ground, where 3I Atlas resides, makes sense for natural processes. We don't fully understand, but requires convoluted reasoning for intentional design. Fifth, timing becomes statistically suspicious. Humanity achieved capability to detect interstellar objects only recently. We've found 3 in 8 years. If artificial objects are common enough that we detect them almost immediately upon looking, the galaxy must be saturated with them. If rare, encountering one during our brief observation window represents remarkable coincidence. Both options strain credulity when aliens are invoked, but make perfect sense if these are natural objects, and we're simply learning how common interstellar debris actually is. The artificial hypothesis also fails to explain observations better than natural hypotheses. Yes, natural explanations face challenges with energy budgets and internal structures, but technology faces equal challenges explaining why an engineered object would display this specific combination of characteristics. Exotic natural. Physics might be poorly understood, but it's known to exist. Alien technology is entirely hypothetical. Science operates on evidence, not possibilities. Anything is possible in the absence of disproof. What matters is what's probable, supported by data, and consistent with broader understanding. Aliens remain the worst explanation, not because they're impossible, but because they're unnecessary, multiply improbable, and explain observations no better than natural processes while introducing unfalsifiable elements. When Carl Sagan said extraordinary claims require extraordinary evidence, this is precisely the situation he meant. The magnetic field discovery triggered the most coordinated international observing campaign in the history of interstellar object astronomy. Within days of the January announcements, space agencies, universities, and private observatories across 6 continents began redirecting instruments toward 3I Atlas. The urgency was palpable. The object was already departing the inner solar system, heading back toward interstellar space. Every day reduced signal strength as distance increased. Every week of delay meant lost data that could never be recovered. The astronomy community mobilized with unprecedented speed and cooperation. NASA reassigned observation time on the Hubble Space Telescope, James Webb Space Telescope, and multiple planetary science missions. the Parker Solar Probe and Solar Orbiter adjusted their telemetry priorities to maximize magnetic field monitoring during windows when orbital geometry brought them near 3I Atlas's trajectory. The Chandra X-ray Observatory searched for high-energy signatures that might reveal nuclear processes or exotic physics. Every available space-based asset with relevant capabilities received tasking orders. The European Space Agency coordinated ground-based observations across its network of partner facilities. Optical telescopes tracked the object's brightness and rotation to correlate with magnetic variations. Radio observatories searched for electromagnetic emissions associated with the magnetic field. Spectroscopic instruments continued monitoring outgassing composition, looking for chemical signatures that might explain internal heat sources. The coordination required precise scheduling, as 3I Atlas's position in the sky changed daily, passing through different observation windows for facilities at various longitudes. Ground-based magnetometers, typically used for studying Earth's magnetic field and space weather, attempted to detect 3I Atlas's field despite the enormous challenge of filtering out terrestrial magnetic interference. Several high-latitude stations in Antarctica and northern Canada, where Earth's field geometry offered slight advantages, reported possible detections during optimal viewing conditions. The signals sat barely above noise levels, but added independent confirmation to spacecraft measurements. Amateur astronomy communities contributed observations that professional facilities couldn't provide due to limited time allocation. Distributed networks of backyard telescopes maintained nearly continuous photometric monitoring, tracking brightness variations that might correlate with magnetic transients. Citizen science projects enlisted thousands of volunteers to analyze images, searching for subtle changes in coma structure or outgassing patterns. The collaborative approach generated data volume that would have been impossible through professional channels alone. International data sharing proceeded smoothly, despite the politically charged nature of some previous space collaborations. Researchers from the United States, Europe, Russia, China, Japan, and India pooled observations through established astronomical databases and informal collaborative networks. The scientific questions transcended geopolitics. This was humanity collectively trying to understand something that challenged fundamental assumptions about the universe. National interests faded against the shared goal of solving a genuine mystery. By late March 2026, over 200 institutions across 40 countries had contributed observations to the 3I Atlas magnetic field database. The dataset represented dozens of instrument types spanning electromagnetic spectrum from radio through gamma rays. Processing and analyzing this flood of information would take months, but the collection phase needed to happen quickly before the object moved beyond detection range. The global response demonstrated what international scientific cooperation could achieve when facing questions that mattered more than politics or priority. The James Webb Space Telescope represented humanity's most powerful tool for chemical analysis of distant objects. Its infrared spectrographs could detect molecular signatures with sensitivity and resolution impossible from ground-based observatories. If 3I Atlas harbored exotic compounds or unusual isotopic ratios that might explain internal heat generation, Webb would find them. The observatory's time was precious, allocated through competitive proposals evaluated months in advance. But the magnetic field discovery qualified as target of opportunity, the kind of urgent science that justified disrupting scheduled observations. Webb's near-infrared spectrograph began dedicated observations of 3I Atlas in late February 2026. The instrument focused on spectral regions where volatiles sublimating from the nucleus produced absorption and emission features. Water, carbon dioxide, carbon monoxide, methane, ammonia, and more complex organic molecules each created distinctive patterns in infrared light. Measuring not just which molecules were present, but their relative abundances and isotopic compositions would constrain formation conditions and potentially reveal heat sources. The first priority involved searching for compounds that shouldn't be abundant if 3I Atlas were a typical comet. Deuterium to hydrogen ratios provided clues about formation temperature and location relative to the parent star. Water molecules containing deuterium instead of normal hydrogen formed preferentially in cold environments. 3I Atlas showed deuterium enrichment at the high end of observed cometary values, but not impossibly so. It confirmed formation in frigid outer regions of some stellar system without requiring exotic explanations. Isotopic ratios of carbon and oxygen told similar stories. The carbon-13 to carbon-12 ratio and oxygen-18 to oxygen-16 ratio reflected nuclear processing in stars and mixing in the interstellar medium before the object formed. 3I Atlas's values fell within observed ranges for solar system comets, suggesting formation from similar raw materials, processed through similar stellar evolution pathways. The chemistry looked alien in the sense of originating in another star system, but not alien in the sense of violating known astrophysical processes. Searches for unexpected compounds focused on species that might indicate internal chemical activity. Complex organic molecules, particularly those containing nitrogen or sulfur in unusual bonding configurations, could suggest ongoing reactions rather than simple sublimation of primordial ices. Webb detected methanol, formaldehyde, and other organics typical of comets. Nothing screamed active chemistry at levels that could generate substantial heat. The most intriguing finding involved trace noble gas emissions. Argon and neon, detected at barely significant levels, appeared depleted relative to solar abundances. Noble gases don't form chemical bonds, so their abundances reflect physical trapping during ice formation rather than chemistry. Depletion suggested formation at temperatures and pressures where these gases remained gaseous and escaped rather than incorporating into ice. The finding hinted at formation conditions slightly warmer than the coldest regions of protoplanetary disks, but still well within bounds for natural comet formation. By mid-March, Webb observations had characterized 3I Atlas's composition thoroughly, without finding smoking gun evidence for exotic heat sources. The chemistry looked like a comet, albeit one formed in another stellar system, under conditions marginally different from solar system comet formation. If unusual internal heat existed, it wasn't leaving obvious chemical fingerprints in the outgassing. The mystery of the magnetic field remained unsolved despite humanity's most sophisticated chemical detective work. Magnetic fields and electric currents create electromagnetic radiation. This fundamental relationship, described by Maxwell's equations, means any object generating active magnetic fields should produce detectable radio emissions. The spectrum and characteristics of those emissions would provide crucial diagnostic information about the underlying processes. If 3I Atlas's magnetic field arose from rotating plasma currents, coherent radio bursts might appear at frequencies related to rotation rates and plasma densities. If thermoelectric currents drove the field, broadband thermal emission would dominate. If something more exotic was occurring, the radio signature might reveal patterns that visible light and direct magnetic measurements couldn't show. Radio telescopes around the world turned their receivers toward 3I Atlas throughout February and March 2026. The Very Large Array in New Mexico monitored frequencies from 1 to 50 gigahertz, covering ranges where planetary magnetospheres and stellar magnetic activity produce characteristic emissions. The Atacama Large Millimeter Array in Chile focused on higher frequencies where molecular transitions from outgassing created spectral lines that could be analyzed for Doppler shifts and intensity variations. The Low Frequency Array in Europe searched for signals below 1 GHz, where plasma processes and magnetic phenomena in space often generate the strongest emissions. Initial observations detected radio emissions consistent with solar-wind interaction with 3I Atlas's plasma environment. As charged particles from the Sun encountered the comet's outgassing, they created a region of disturbed plasma that emitted radio waves through well-understood processes. The intensity varied with solar wind conditions as expected. This was the radio equivalent of background noise, interesting for plasma physics, but not revealing about internal magnetic field generation. Searches for periodic or transient radio signals required more sophisticated analysis. Researchers recorded continuous data and performed time series analysis, looking for signals that repeated at specific intervals or appeared suddenly above background levels. The 5.3-hour and 12.7-hour magnetic field periods became particular targets. If those periodicities reflected rotating structures or oscillating currents, radio emissions might pulse at the same rates. Weeks of observation produced tantalizing hints, but no definitive detections. Several observing runs showed excess radio emission near 5.3-hour intervals, but the signals appeared and disappeared inconsistently. Statistical analysis couldn't rule out random fluctuations in background noise. Other observations showed nothing unusual at all. The inconsistency suggested either the radio emission was real but intermittent, tied to viewing geometry or internal processes that operated sporadically, or the detections were false positives in noisy data. High-time resolution observations searched for millisecond to second scale bursts, the kind of rapid transient that might accompany magnetic reconnection events or sudden current surges. Several candidate events appeared during coordinated optical and radio monitoring campaigns, but without independent confirmation from multiple facilities or clear correlation with magnetic field transients observed by spacecraft, the radio bursts remained ambiguous. They could be terrestrial interference, ionospheric effects, or genuine signals from 3I Atlas. Distinguishing between these possibilities required more data than the limited observation windows provided. Radio astronomy added pieces to the puzzle without completing the picture. 3I Atlas existed in the radio spectrum, producing emissions from its plasma environment. Whether it also produced radio signatures of internal magnetic field generation remained uncertain. The absence of strong, unambiguous radio signals suggested either the field generation process didn't produce readily detectable radio emissions, or those emissions existed at frequencies or intensities that current observations couldn't reach. Distance is the enemy of observation. every day that passed after 3I Atlas's closest approach to the Sun on December the 19th, 2025, carried the object farther from Earth and deeper into the outer solar system. By late March 2026, it had crossed Mars's orbit outbound, continuing its journey back toward interstellar space. The increasing distance weakened every signal, dimmed every observation, and reduced the quality of data that instruments could collect. Time was running out. Magnetic field strength follows an inverse cube law for dipole sources. Double the distance, and field strength drops to 1/8. The Parker Solar Probe's initial detection at 10 million kilometers already represented the limit of magnetometer sensitivity. As 3I Atlas receded, fewer spacecraft could detect its field at all. By April, only the most sensitive instruments during closest approach windows registered anything above noise. By May, direct magnetic field observations would become impossible until some future mission ventured close enough, which might never happen given the object's departure trajectory. Optical brightness faded according to inverse square law for reflected sunlight. 3I Atlas was moving away from both the Sun and Earth simultaneously, receiving less illumination and appearing dimmer from our perspective. Photometric monitoring that tracked brightness variations for rotation and outgassing studies required longer exposure times as the object faded. Background stars that were faint nuisances in February became significant noise sources by April. Small telescopes lost the object entirely. Even major observatories found observations increasingly challenging. Spectroscopic analysis suffered worst of all. Breaking light into spectra for chemical composition studies spreads photons across many wavelength channels, reducing signal in each channel proportionally. The high-resolution spectroscopy that revealed molecular abundances and isotopic ratios required bright targets. Webb could still observe 3I Atlas through April, but with degrading signal-to-noise ratios. By May, even Webb's sensitivity would struggle to detect weak spectral features. The window for detailed composition studies was closing rapidly. The astronomy community faced painful prioritization decisions. Every telescope had competing demands from other scientific programs. Continuing 3I Atlas observations meant delaying other projects, some planned years in advance. How much telescope time was justified for an object that was providing diminishing returns as it faded? Different institutions reached different conclusions. Some maintained monitoring through May and beyond, accepting degraded data quality to extend temporal coverage. Others concluded that by April, the useful observation phase had ended and released telescope time back to scheduled programs. Researchers began intensive analysis of accumulated data, recognizing that new observations would soon become impractical. The race shifted from gathering more data to extracting maximum information from what already existed. Papers entered peer review, describing magnetic field properties, chemical composition, rotation characteristics, and attempts to model internal structure. The conversation evolved from what we're currently observing to what we managed to learn before the opportunity passed. 3I Atlas would remain visible to the largest telescopes for months, a fading dot among countless stars. But the brief window when detailed study was possible had already closed. By summer 2026, the object would be effectively beyond reach, carrying its mysteries back into the darkness between stars. Whatever we hadn't learned by then might remain unknown until another interstellar visitor arrived. whenever that might be, bringing its own questions and perhaps some answers to those 3 I-Atlas left behind. 3 I-Atlas's magnetic field discovery forced astronomers to reconsider everything they thought they knew about interstellar visitors. If one object could generate active magnetic fields, what about the others? Oumuamua and 2I Borisov had been observed extensively, but nobody was looking for magnetic signatures. The spacecraft that could have detected such fields weren't positioned correctly, or the relevant data hadn't been analysed from that perspective. Suddenly, archived observations from previous interstellar visitors gained new importance as researchers searched for clues they'd missed the first time. Oumuamua presented the most intriguing case for reanalysis. That elongated visitor's anomalous acceleration as it departed the solar system in 2017 had spawned years of debate. Outgassing seemed insufficient to explain the trajectory changes, yet no magnetic field measurements existed to test whether electromagnetic effects might play a role. Could Oumuamua have possessed an active magnetic field that interacted with the solar wind in ways that affected its trajectory? The hypothesis remained speculative without data, but it suddenly seemed worth investigating whether archived solar wind measurements showed disturbances that correlated with Oumuamua's position. 2I Borisov behaved so conventionally that it barely generated scientific controversy beyond confirming that interstellar comets could look exactly like solar system ones. But conventional appearance didn't guarantee conventional internal structure. The object received less intensive study than Oumuamua precisely because it seemed unremarkable. No spacecraft passed close enough for magnetic field detection. Ground-based observations focused on composition and activity rather than electromagnetic properties. If 2I Borisov possessed magnetic fields weaker than 3I Atlas or generated them intermittently, the signals could have been missed entirely. The realization extended beyond specific objects to general detection capabilities. Most astronomical observations focus on electromagnetic radiation, gathering light across various wavelengths to study composition, temperature, motion, and structure. Direct magnetic field measurements require spacecraft with magnetometers passing within detection range. For typical objects in the solar system, this happens routinely as missions visit planets, moons, and occasionally asteroids or comets. For interstellar visitors appearing unpredictably and moving rapidly through the inner solar system, close approaches with appropriately instrumented spacecraft are rare coincidences. 3I Atlas benefited from fortunate timing. Multiple spacecraft with sensitive magnetometers happened to occupy positions where their orbital trajectories brought them within detection range during the months when the interstellar visitor passed through the inner solar system. Parker Solar Probe and Solar Orbiter weren't designed to study interstellar objects, but their solar observation missions placed them in the right locations at the right time. Without that coincidence, the magnetic field might have gone undetected entirely. How many previous interstellar visitors possessed similar properties, but passed through our detection net unseen? Population statistics became even more uncertain than before. Estimating how many interstellar objects traverse the solar system depends on understanding what we're capable of detecting. If objects can possess properties like active magnetic fields that require specific instrument configurations and observing geometries to reveal, our detection efficiency drops dramatically. The 3 detected interstellar visitors might represent a tiny fraction of actual traffic, with the majority passing through unnoticed because they don't happen to create bright comets or pass close enough for detailed study. 3I Atlas suggested the interstellar debris field contained more diversity than simple extrapolations from solar system objects predicted. Magnetic field generation requires specific conditions that constrain where and how 3I Atlas could have formed. Every hypothesis about internal structure and energy sources implies something about the object's birth environment. By working backward from observed properties to formation requirements, astronomers could narrow the possibilities about which stellar system spawned this mysterious visitor and what processes shaped it billions of years ago. The high carbon dioxide to water ratio detected by JWST indicated formation beyond the carbon dioxide snowline, regions so cold that carbon dioxide freezes alongside water ice. In our solar system, this boundary sits around 5 astronomical units from the Sun, roughly Jupiter's orbit, but snowline positions vary with stellar luminosity and evolution. Around dim red dwarf stars, the carbon dioxide snowline could exist much closer. Around young massive stars, it would move farther out. 3I Atlas's chemistry suggested formation in the outer reaches of whatever planetary system birthed it, perhaps tens of astronomical units from the parent star. If the object required radioactive heating to maintain internal activity, formation timing became critical. Short-lived isotopes like aluminum-26 exist only in young stellar systems, injected by nearby supernova and decaying within millions of years. 3I Atlas would need to have formed while its parent star was less than 10 million years old to incorporate sufficient short-lived isotopes. This implied formation in a dense stellar nursery where supernova occurred nearby, enriching the raw material with fresh radioactive elements. Alternatively, if magnetic field generation relied on exotic internal structures created during differentiation, the object must have experienced heating sufficient to melt and reorganize its interior. This could happen through radioactive decay early in its history, or through energetic collisions during formation. Either scenario required a more violent birth environment than the gentle accumulation typically envisioned for comet formation. Perhaps 3I Atlas formed closer to its parent star, where temperatures and collision rates were higher before gravitational interactions ejected it outward and eventually into interstellar space. The ejection mechanism itself provided clues. Removing an object from its birth system and accelerating it to interstellar speeds requires specific dynamical configurations. Close encounters with giant planets can do this, slingshotting smaller bodies outward with sufficient velocity to escape stellar gravity. If 3I Atlas formed in a system with massive planets orbiting beyond the snowline, similar to our Jupiter and Saturn, such encounters become plausible. The object's formation location and ejection mechanism might be linked, both reflecting the architecture of its parent planetary system. Some formation scenarios invoked environments unlike anything in our solar system. Perhaps 3I Atlas originated in a binary star system where complex gravitational dynamics and dual heating sources created unusual conditions. Or it might have formed in the debris disk of a stellar collision, an environment rich in exotic chemistry and energetic processes. White dwarf systems, where dying stars create unique chemical and thermal environments, offered another possibility. Each exotic scenario explained some observations, while raising new questions about probability and prevalence. The magnetic field transformed 3I Atlas from an interstellar object we could observe into a puzzle we could decode for information about galactic diversity. Every characteristic carried information about formation environments humanity would likely never visit directly. This wanderer from another stellar system brought messages written in magnetism and chemistry, telling stories about processes operating throughout the galaxy. Reading those messages required recognizing that our solar system might not represent the only way planetary systems evolve and eject their debris into the cosmic ocean. Before 3I Atlas, astronomers had a population statistics headache. The object's enormous mass violated expectations that smaller interstellar visitors should be discovered first. Ejection mechanisms favor lighter objects, requiring less gravitational energy to accelerate them to escape velocity. Detection should preferentially reveal the numerous small visitors before rare massive ones. Yet the third, confirmed interstellar object was potentially the largest, creating a population puzzle that defied simple explanations. The magnetic field discovery transformed a headache into a migraine. Now, 3I Atlas wasn't just unexpectedly massive, but also electromagnetically active in ways that natural processes struggled to explain. If this represented typical behavior for interstellar objects, rather than a unique anomaly, the entire framework for understanding galactic debris needed revision. If instead, 3I Atlas was genuinely one of a kind, its early detection became even more statistically improbable. Consider the numbers carefully. Astronomers had systematically searched for interstellar visitors for only 8 years since Oumuamua's discovery in 2017. In that brief window, they found 3 objects. Simple extrapolation suggested dozens or hundreds might pass through the inner solar system annually if detection capabilities improved. But that extrapolation assumed detected objects represented typical examples from a larger population, distributed according to predictable mass functions based on ejection physics and collisional evolution. 3I Atlas broke those assumptions. If massive magnetically active objects constituted a significant fraction of interstellar traffic, where were the inactive ones? Where were objects with intermediate masses between 2I Borisov's modest size and 3I Atlas's bulk? The distribution appeared bimodal or worse, showing extremes without a smooth continuum. Natural populations rarely display such gaps unless selection effects create artificial patterns or multiple distinct populations exist with different origins. Selection effects could explain part of the puzzle. Perhaps massive active objects were easier to detect because their outgassing created bright visible comas that automated surveys found readily. Smaller inactive visitors might pass through unnoticed unless they happen to transit particularly well-monitored sky regions. But this explanation struggled with 3I Atlas's magnetic properties. Those required spacecraft magnetometers for detection, instruments that don't contribute to visual discovery. The object would have been found based on its optical signature, regardless of magnetic behavior. Alternative explanations invoked multiple interstellar object populations. Perhaps typical debris ejected through standard planetary dynamics constituted one population, small and inactive, like 2I Borisov. Rare catastrophic events like stellar collisions or white dwarf disruptions might create a second population of unusual massive active objects. 3I Atlas could be sampling this exotic population, which exists at much lower number density, but stands out when detected. The early discovery of a rare object type would be unlikely, but not impossible, if the rare population had distinctive observable properties. The timing of humanity's first systematic interstellar object surveys created observer selection effects. We started looking seriously only after achieving detection capabilities adequate for finding these visitors. Any statistics based on 3 detections in 8 years had enormous uncertainties. Perhaps the next decade would reveal dozens of objects, clarifying whether 3-eye atlas represented outliers or typical examples. Or perhaps discoveries would remain rare, each one unique, challenging attempts to build population models from such sparse data. 3-eye atlas deepened mysteries instead of resolving them. Each new characteristic added complexity to population questions. The object existed, undeniably real and thoroughly observed. Whether it represented a common class we'd barely begun sampling, or a genuine anomaly that challenged fundamental understanding, remained frustratingly uncertain. Only time and more discoveries would tell. Planetary defense focuses on identifying and tracking objects that might collide with Earth. Asteroids and comets from our solar system receive the most attention because their orbits are predictable and impact probabilities can be calculated decades in advance. Interstellar visitors complicate this picture significantly. They appear with little warning, traveling on hyperbolic trajectories that carry them through the inner solar system once before departing forever. 3-eye atlas's magnetic field added another layer of complexity to an already challenging problem. Active magnetic fields imply internal processes that could affect trajectory predictions. Standard orbital calculations assume objects follow paths determined solely by gravity and solar radiation pressure. Outgassing creates small non-gravitational forces that nudge comet orbits slightly, effects that astronomers account for through empirical models based on observed activity. But magnetic fields interacting with the solar wind could produce additional forces that current models don't include. If an incoming interstellar object possessed a strong magnetic field, trajectory predictions might accumulate errors over weeks or months of approach. The magnitude of magnetic effects on trajectories depends on field strength and solar wind conditions. 3-eye atlas's field created a magnetosphere extending perhaps thousands of kilometers from the nucleus. Solar wind particles deflecting around this magnetosphere would transfer momentum to the object through electromagnetic forces. Calculations suggested these forces were orders of magnitude weaker than gravity and solar radiation pressure, probably too small to significantly alter trajectories over timescales relevant to Earth impact scenarios. But probably isn't the same as certainly, especially when dealing with objects whose internal properties remain poorly understood. Detection becomes the primary challenge. Earth-crossing asteroids can be discovered years before potential impacts through systematic sky surveys. Objects from our solar system orbit the Sun predictably, appearing at expected locations that telescopes can monitor. Interstellar visitors arrive from random directions with no advance warning. Oumuamua was discovered after closest approach to the Sun, when it was already leaving. 2-eye Borisov provided a few months' notice. 3-eye Atlas was found half a year before perihelion. The detection timeline depends on object size, activity level, and whether it passes through well-surveyed sky regions. An interstellar object on collision course with Earth might provide insufficient warning time for deflection missions. Current planetary defense concepts require years to design, build, and launch spacecraft capable of nudging hazardous asteroids onto safe trajectories. Months of warning wouldn't allow such missions. Evacuation of impact zones might be the only option if an interstellar visitor threatened populated regions. The probability of such an event remains extremely low, given the vastness of space and Earth's small cross-section. But 3I Atlas demonstrated that interstellar objects can be massive and possess unexpected properties. The magnetic field discovery highlighted gaps in planetary defense frameworks. Current threat assessment models assume objects behave according to solar system experience. Interstellar visitors might not follow those rules. As humanity's detection capabilities improve and more interstellar objects are discovered, planetary defense planning will need to incorporate the possibility that some visitors possess characteristics requiring updated prediction and mitigation approaches. 3I Atlas provided no immediate threat, but raised questions about future visitors that might. By April 2026, 3 months after the magnetic field discovery, the scientific picture remained frustratingly incomplete, but dramatically richer than initial observations suggested. 3I Atlas had transformed from an interesting interstellar comet into a natural laboratory testing the boundaries of planetary science. What we learned wasn't always what we hoped to learn, but every observation added detail to a phenomenon that defied easy categorization. The magnetic field's reality was no longer in question. Multiple independent spacecraft measurements from different viewing geometries confirmed an intrinsic dipolar field emanating from the object itself. Peer review of initial papers proceeded smoothly, with reviewers praising observational rigor, while noting that interpretation remained contentious. The field strength estimates solidified around 50 to 100 microtesla at the surface, roughly comparable to Earth's equatorial field, despite the vast size difference. This represented established fact rather than preliminary claim. Temporal variations showed consistent patterns across the observation period. The 5.3 and 12.7 hour periodicities persisted through March, neither strengthening nor weakening substantially as the object receded from the Sun. Several dozen transient events were documented with varying intensities and durations. The quasi-periodic nature suggested organized internal processes rather than random fluctuations, but identifying those processes remained elusive. Natural explanations couldn't be ruled out, but none fit observations without substantial assumptions. Chemical analysis from JWST and other spectroscopic observations painted a picture of relatively normal cometary composition, with unusual enrichment in carbon dioxide and depletion in noble gases. Nothing in the chemistry screamed exotic heat sources or active internal reactions. The disconnect between ordinary composition and extraordinary magnetic behavior deepened the mystery. Either the magnetic field generation required only modest energy inputs that wouldn't dramatically alter bulk chemistry, or it operated through processes that didn't depend on unusual chemical compositions. Energy budget calculations remained problematic. Every conventional power source fell short of requirements by factors ranging from 10 to thousands, depending on assumptions about field generation efficiency. Unconventional sources, including exotic radioactive concentrations, quantum effects, or internal structures, unlike anything in solar system experience couldn't be definitively ruled out, but lacked supporting evidence. The gap between observed output and identified input persisted as the central unsolved problem. Competing hypotheses sorted into rough categories without clear winners. Natural explanations invoking poorly understood but physically plausible processes maintained strong support among researchers committed to conventional science. Exotic natural scenarios incorporating elements at the boundaries of known physics attracted minority support, with advocates arguing that interstellar environments might enable processes that solar system objects never experience. The techno-signature hypothesis remained firmly in the fringe, maintained by a few researchers willing to explore uncomfortable possibilities, while acknowledging the extraordinary evidence burden such claims required. What everyone agreed upon was that 3I Atlas revealed gaps in understanding. Whether those gaps reflected incomplete knowledge of natural processes or genuine anomalies pointing toward new physics or even artificial origin remained the subject of intense, ongoing debate. The object had done what great scientific mysteries do, forcing researchers to question assumptions, improve observational techniques, and think more carefully about what they thought they knew. The learning wasn't finished. Papers would appear for years, analysing archived data and debating interpretations. But the primary observation phase was ending as the object faded from view, carrying answers back into interstellar darkness. 3I Atlas began its journey back toward interstellar space, speaking in a language humanity had only recently learned to hear. The magnetic field that shouldn't exist pulsed with rhythms that defied simple explanation, broadcasting across millions of kilometers through electromagnetic force. The silent giant, whose mass anomaly had already challenged understanding, found its voice in the most unexpected way. And that voice raised more questions than it answered, leaving behind a mystery that would echo through astronomy for generations. By May 2026, the object had faded beyond detailed observation for all but the most powerful telescopes. The bright comet that dominated headlines in late 2025 was now a dim speck, indistinguishable from background stars without careful tracking. The magnetic field signal had dropped below detection thresholds as distance weakened it past instrument sensitivity. 3I Atlas was effectively gone, departing as mysteriously as it arrived. But the impact of its brief passage would reshape how humanity thinks about the space between stars. The legacy extends beyond unanswered questions about magnetic field generation. 3I Atlas demonstrated that interstellar objects can possess properties that challenge fundamental assumptions about how matter behaves in space. Whether the explanation ultimately proves to be exotic natural physics, gaps in understanding conventional processes, or something even more extraordinary, the object forced acknowledgement that our cosmic neighborhood contains surprises waiting to be discovered. The universe operates on scales and through mechanisms that still exceed human comprehension, despite centuries of scientific progress. Future interstellar visitors will be observed differently because of 3I Atlas. The next object detected will face immediate questions about magnetic properties, internal structure, and energy sources that wouldn't have been asked before. Spacecraft missions designed for solar system exploration will include protocols for opportunistic interstellar object observation. Ground-based surveys will coordinate with space-based magnetometers to catch electromagnetic signatures early. The astronomical community learned from this experience, recognizing that each visitor might be unique and that assumptions based on solar system experience could miss crucial phenomena. The Vera Rubin Observatory, scheduled to begin operations in 2025, will discover dozens, or potentially hundreds, of interstellar objects, annually once fully operational. That flood of detections will provide statistical context that 3 isolated examples cannot. Perhaps 3I Atlas will prove to be a common type, representatives of a population that our limited sampling simply hadn't captured yet. Perhaps it will remain unique, a genuine outlier that appeared during humanity's first stumbling attempts to study interstellar traffic systematically. Either outcome teaches us something profound about galactic processes and the diversity of objects wandering between stars. In the end, 3I Atlas embodied the essential excitement of scientific discovery. It arrived unexpected, defied explanation, and departed with mysteries intact. The silent giant spoke, and humanity listened carefully, learning that listening itself was valuable even when the message remained only partially understood. The next interstellar visitor approaches even now, somewhere in the darkness, carrying its own secrets. We watch the skies and wait, instruments ready, minds open, prepared to be surprised again by a universe that refuses to run out of wonders. The conversation between humanity and the cosmos continues, one mysterious visitor at a time.